Hello, chemists. Thank you for joining me on this Snow Day lecture series where we will be talking about Chapter 4 material, so Introduction to Organic Compounds. So we're expanding on the idea of molecules in our molecular naming compounds. Remember, with molecular naming, we have all nonmetals that make up those compounds. So we're expanding on that within organic chemistry, where we have all nonmetals making our molecule. So organic chemistry, sometimes called the chemistry of life, and I use air quotes because it's not quite true, and you'll see why in a minute. All right, so what we will be talking about in Chapter 4 is how we can represent organic compounds with not just Lewis structures, but other types of formula to convey structure to other chemists. We'll look at some simple families of organic compounds that you'll commonly run into in the pharmaceutical industry and in everyday life. We'll look at, in the second part of the chapter, we'll look at naming and isomerism, so how these structures exist in three-dimensional space, and how our bodies can interpret those. So note here, there are some things that you need to memorize in this table, so you can see those there. Some of our naming prefixes for alkanes and the names of their substituents and functional groups. So this is not an exhaustive list, but these are some things, when I was making these slides, that you definitely need to memorize. Okay, so when we think of organic chemistry, or just the term organic, we're all humans, and we have this idea like, organic foods and labels such as these. But as organic chemists, that's not what we mean, all right? So oftentimes when we see the, USDA organic label, we think like, oh yeah, living, we have substances or foods that are unadulterated. They just come from the earth and such. But within organic chemistry, actually everything that you see in this picture is an organic molecule, except the metal of this gas container. Everything else, the plastic that you see, the medicines that you see here, even Vaseline, they're actually organic compounds. And what they all have in common here is that they contain carbon, hydrogen, oxygen, or nitrogen, and other nonmetals. So when we think about organic within chemistry, that's what we're thinking of, things that are composed of those elements. Okay, so not the organic labels that we see at the grocery store. That's completely different. But there is some overlap, and you can kind of see that in this evolution of organic chemistry and where that name came from. So early on, so this is Friedrich Wöhler, and we call the father of organic chemistry. So before his time, when chemists thought of organic chemistry and we separated it from inorganic chemistry, meaning metals and metalloids, they just thought that organic chemistry, these are molecules and compounds that just came from living or once living animals and living beings, that these are the molecules that they produced. But Friedrich Wöhler did an experiment where he took an inorganic substance, so ammonium cyanide. So if you write out the chemical formula for ammonium cyanide, you should recognize that that is an ionic compound. So, and it's inorganic in a sense, but he decomposed this compound and produced urea. And so he made the connection that he turned this inorganic substance into another substance that occurs naturally in living beings. So urea is one of the chemicals in urine. And so he kind of proved that, no, there's something a little bit more subtle here, that these inorganic substances can still make or decompose into what we think of as an organic compound. So the definition of organic chemistry became more broad and more about the composition of substances. So now the definition of organic chemistry is just compounds that contain mostly carbon and hydrogen. We are carbon beings, carbon-based beings here on Earth. And so carbon and hydrogen is the majority of the elements within organic chemistry, but there are a lot of other nonmetals as well, such as oxygen, nitrogen, phosphorus, and some of the halides. But what all of these have in common is that they are nonmetals. And then within or inorganic chemistry, so the opposite of organic chemistry, it's just everything else, so metals and metalloids. Okay, so within organic compounds, there's so many that we interact with in our everyday life. They make up our bodies, we take them as drugs, we the foods that we eat, All those are made of organic compounds, and they're all based on the element carbon. So carbon is really the backbone here of organic chemistry. So let's just recall some facts that we know about carbon from chapter 3. Carbon, based upon our periodic table, okay, yep, you can see that, is in group 4A. Let's recall that. It's in group 4A, so it has 4 valence electrons. And typically, carbon will share 4 of its electrons with other atoms in order to achieve its full octet. And so when carbon shares electrons, it forms 4 other bonds in total, so there are a total of 8 electrons around that whole carbon atom. Carbon, we've seen, can form either single, double, or triple bonds to other atoms, and we see carbon in different shapes, from last chapter when we predicted shape, tetrahedral, trigonal, planar, or linear. And these covalent bonds, the sharing of electrons with carbon in particular, those bonds are quite strong. So in these pictures, I think we've seen these before, but we see all of the different connectivities of carbon in these pictures. You should be able to identify each carbon center with a specific geometry. This carbon is tetrahedral. All right, this next one, because there's just 2 atoms or 2 charge clouds around that carbon, it's linear, and so is the next one. Both of those are linear. Well, this first one has 4 charge clouds around it, so it's tetrahedral, while in this other compound, both of these carbons are trigonal planar, because there are only 3 other atoms around each carbon atom. All right, and so even though we draw this Lewis structure, it looks like it's a T shape. It's not. Recognizing that electrons will spread out to give each other as much room as possible, it's actually 120 degrees from one another, not the 90 that you see in this 2-dimensional picture. All right, so how organic chemists represent organic molecules, or just chemists in general. We already know molecular formulas. That's what you see here for propane. So molecular formulas just tell us the exact number of atoms of each type in one molecule. So that doesn't give us a good picture of what those substances look like. So chemists come up with other ways to give more information about the structure of these complex compounds. So the molecular structure just tells us the composition. Remember that. So it doesn't tell us anything about composition. Yeah. It doesn't tell us anything about how the atoms are connected. But the condensed structure, the next one that you see, does tell us a little bit more about how the carbon chain propagates, and then the Lewis structure gives us the most information about connectivity of all the atoms and bonds here. So the condensed structure, you'll see that a lot. It shows some of the bonds of the atoms, or it shows all the atoms, but not necessarily all the bonds. So what you see here, how the condensed structure and the Lewis structure are related. So if you look at each carbon center on our Lewis structure, you can kind of see that being mirrored in our condensed structure, that the first carbon has 3 hydrogens attached to it. So that's kind of what you see here. The next carbon has 2, because it's CH2, has 2 hydrogens, and then the last one has 3. So if you kind of box them like this, you can see that this is CH3. This component, the second carbon, is CH2, and the next one is CH3. So you can see how the condensed structure and the Lewis structure are related in that way. And Lewis structures, this is very difficult to write on a computer, in a Word document, but the condensed structure is something that you could easily write in a Word document, but will give much, much more information structurally than just a molecular formula. All right, and so the last type of way that organic chemists use structures to communicate structure and composition is skeletal structures for carbon-containing compounds, and this is the most used. When you see papers of organic compounds, organic chemistry, or if you see them in textbooks, you will oftentimes see skeletal structures, and it's mostly lines. So we need to recognize and learn how to read these lines in these skeletal structures. So in these structures, it's the most simple. And so the biggest idea with skeletal structures is that, with a Lewis structure, there's a lot of hydrogens, right? If we look at this Lewis structure, there's a lot of hydrogens. The hydrogen is like the simplest atom, the simplest element, right? So what a skeletal structure does is kind of get rid of that spinach in the structure and just focuses on what is important, and that is the carbon chain. So with skeletal structures, we show all the bonds except the ones to hydrogen. And so all of the carbon-hydrogen bonds are implied. And so you should be able to you had to figure out how many carbons were on a skeletal structure, you could figure it out because you know that carbon always forms 4 bonds. So if we look at the skeletal structure, all right, so each either end or joint of a line is a carbon atom. So there's a carbon atom here, here, and here. So this skeletal structure and this Lewis structure is trying to show the same exact thing. I know that this carbon on the end, it needs 4 bonds. There's only 1 bond drawn for the other carbon, the carbon-carbon bond. So it would be implied that there are 3 other hydrogens there. And then the middle carbon, because there's 2 bonds to it, would have 2 hydrogens. And then the last one would have 3 hydrogens as well. So we get rid of all of the hydrogens in skeletal structures to just show the carbon backbone. And why that's important, and when we do it in this zigzag pattern, is because the skeletal structure is the most similar to what the actual molecule looks like. So the Lewis structure drawn here, it kind of looks like the molecule is straight. If a reader didn't know much about the geometry and molecular shape of carbon atoms, they might just think that this is that propane is like a flat molecule, but it's not. We know that each of these carbon centers is tetrahedral. And so in lab, you will build one of some organic molecules and see that when all of the carbons are tetrahedral centers, right? So that's what you see here in this ball and stick model. They take on these bench shapes that you see this zigzag pattern. So that's what you see here. So if you look closely, each carbon center, each black ball, which also represents, either an end or a joint of our skeletal structure, is a carbon atom. And then you can see those hydrogens put back in there. So skeletal structure is the most similar to the real structure, but we ignore the hydrogen atoms within there. But they are implied. All right, so it's not like they disappear. They're just implied. All right, so rules for looking at skeletal structures and how to draw them. So recognize there's a carbon atom at each joint or end. We don't draw the carbon hydrogen bonds within there. So we're just kind of focusing on that the carbon chain, the carbon backbone. If there are other elements bonded to carbon, which we will describe later, those are heteroatoms, you draw the bonds for those. And then oftentimes lone pairs, like on halides or something, so like on chlorine, typically you don't draw them, but you know that they're there, that chlorine has a total of 7 valence electrons and that there would be 3 lone pairs on that atom. So for drawing a skeletal structure, first you need to recognize how many carbons are in the chain connected end to end. So here's a different molecule, so 4 carbon chains. So you need to make sure that you have a total of 4 either joints and ends total. So in this picture, it's trying to show you, okay, if you draw 4 points staggered from one another and then draw the bonds in there, there is your 4 carbon chain within there. So you need to have a total of, it's not the number of lines, right? So if we drew this out as a skeletal structure, you see there's only 4 lines, but recognize that each end or each joint is a carbon atom and that there would be implied hydrogens there. And you also have to draw any non-carbon atoms. So in the second example here, you should be able to see that there are 3 carbons in a chain. So 1, 2, 3. All right. And so you would have to draw that OH bond within there. So the carbon to oxygen bond. So what this structure is missing is that OH within there. And really how a organic chemist would draw this is they would draw the 3 carbon backbone and then they would draw OH within there. And recognize oxygen actually has 2 lone pairs on it as well within there, but sometimes structures don't include them because we should recognize that oxygen would need those lone pairs. Also, oxygen typically makes 2 bonds. So that's how we draw skeleton structures. So let's practice a little bit. So identifying the length of the carbon and making sure that we have enough lines to represent all the carbon atoms that are there. So let's look at this condensed structure and draw what the skeleton structure would look like. So I see that there's 1 carbon and 1 on the end, and then there's actually 3 carbons in the middle here. So really the full expanded condensed formula, whoops, not 3, 2. There would be 3 of these CH2s in a row, and then there's that last CH3. All right, so those 3 CH2s are represented right there. And so now you can clearly see that there's 1, 2, 3, 4, 5 carbon atoms in a row. So that's what we want to show in our skeleton structure. So how I'll go about this is think 1, 2, 3, 4, 5. They're my 5 carbons, and I staggered them a little bit because this is how it looks like in real life, and then draw bonds to all of them. And so we would be done there. That's how we represent this, this molecule. So 1, 2, 3, 4, 5, it's pentane. And we'll talk about naming in a little bit. That is one thing that you should be memorizing. Here. All right, so let's do this one. So identify the length of the carbon chain. So I see that there's 2 carbons. All right, and then a bromine at the end. So I'll do that as well. So 2 carbons, all right? Okay, so there we go. And then we have to draw that last bromine, and so we have to draw a bond to it. So that is what that molecule would look like, 1-bromoethane. All right, and so this last one's a little bit tricky, but still the same idea. We identify the length of the carbon chain, 1, 2. So there's an OH, so a different group. And then our third one within there. All right, so let's draw our carbon chain, 3 in a row. So 1, 2, 3. So there's our carbon chain within there. And so what we have to draw, so we're not drawing the hydrogens like we did in the other example, but we do have to show that OH. And so inspecting this, it looks like this OH is connected to the second carbon, because if it was connected to the first or the third one, it would, this OH group would be, you know, either over here or over here. So this is implying that this OH group is connected to this carbon. So we're going to draw that right here. Okay, so the O to the H. All right, and whether you draw it this way or if you draw it this way, that's all right. It would be the exact same. All right, and then that oxygen would have lone pairs, but we don't have to draw it because this is a skeleton structure. All right, so there's some practice for you. All right, so let's go into the details of types of organic compounds that you will interact with in everyday life. So alkanes is the simplest kind of organic compound. We drew one alkane already. So this, the simplest one where we just have carbons and hydrogens, and all the carbons have 4 bonds to them, those are alkanes, right? So we typically call alkanes hydrocarbons. Alkanes is what is in our gasoline. You know, octane is actually a carbon chain of 8 oxygens in a row. So alkanes only contain carbon and hydrogens where there are only single bonds. So recognize that carbon always has 4 bonds to it. And so in alkanes, they're all single bonds. Specifically, we can look at straight chain carbons. So we already drew some straight chain carbons when they're all in a row, all staggered like that. And they are atoms, next to one another, and they form a continuous line. We can also have branched types of alkanes, which we'll look at in a little bit. So how we name alkanes, and the reason we're starting with alkanes is oftentimes the parent name comes from the alkane or the number of carbons. See, carbon is so important in organic chemistry. So recognizing the number of the carbons in the chain is what gives us the name of the structure, the prefix. So methane, ethane, propane, what you see here. Those prefixes, meth, eth, and prop, tell us how many carbons are in that chain. And so what is kind of consistent with all of these examples, all alkane names will end in the ending ane, alkane. So it ends in ane. All right, so methane, what we'll see here on the next slide, that's the table of prefixes that you need to memorize. Methane means 1 carbon, so it has the formula CH4, so just 1 carbon. So I guess, if to draw the skeletal structure of methane, it would technically just be a dot. But typically we don't draw a skeletal structure for methane. So ethane, 2 carbons. All right, so it would be CH3, or it would have a skeletal structure that's just a line, so there's a carbon right there and right there. Propane is 3 carbons, so it has the formula CH3, CH2, CH3, and we need 3 carbons. It would look like this. All right, that's a really bad drawing, but you get the picture. You see that there's 3, not segments, but 3 either ends or joints within there. Right, so those are some of our examples of alkanes, the simplest kind. So that's where a lot of our parent names come from. These prefixes mean the number of carbon atoms within that chain. And so you can see here the condensed formulas that I wrote for all of those and their skeletal structures. So the note is, do you have to memorize these structures too? Not really. As long as you know how many carbons are in a chain, you should be able to build the skeleton structure. And then from there, you can get the condensed structure because you know that each of these carbon atoms that are drawn here need four bonds total. So typically if a carbon's on the end, it needs 3 other hydrogens. So these two need 3, while anyone in the middle, a carbon in the middle, only needs 2 hydrogens. So from there, as long as you know the carbon chain length, you can kind of back figure out what is the condensed structure and then what is the molecular formula, so just the number of carbons and hydrogens. So if we go back to this example here, so I have the condensed structures for these 3, but if we wanted to just write the molecular structure, so just kind of combine everything, it already is for methane, for methane, but for ethane, the formula for ethane would be C2, because there's 2 carbons total, and H6, while propane would be C3H8. So total of 8 hydrogens there. All right, so yes, definitely memorize these prefixes and how we get the names. If it's an alkane, just all single bonds to hydrogen, it ends in the word ane with the prefix. And then from there, you can get the skeletal structure and condensed structure. So all of these examples are straight chain carbons, straight chains. They're all just connected one after one another. So there's other ways we can form carbon, hydrogen containing molecules. We can put them in a ring. And thankfully, the naming scheme makes a lot of sense here. It's all about the number of carbons, before it was in a chain, but now we can think about putting those carbons in a ring instead. So these are cycloalkanes. So it's still called an alkane because all of the carbons and hydrogens are singly bonded, but we add the prefix cyclo to indicate that it is a ring. And so the naming scheme here comes from the number of carbons that are in the ring. In nature, typically 5 and 6 rings are 6 carbons in a ring are the most common. So you won't, this is kind of cute, the skeletal structure for cyclopropane, but you won't see that too often in real in nature. So what you see here in all of these structures, so our rules for skeletal structure still apply here. So we can see here that there are 3 joints. So that means that there are 3 carbons in this chain. So that's why we call it cyclopropane. So you can see the prop prefix still within there to mean 3 carbons. So all of those prefixes still apply here. So if we expand the ring with 4 carbons, it becomes cyclobutane, then cyclopentane, and then cyclohexane. And so still keeping in mind that every carbon needs 2 hydrogens on it. So if we look at cyclobutane, so if we look at this carbon, it already has 2 bonds to other carbons, so it needs 2 hydrogens. So all of these carbons have 2 hydrogens on them. So if we actually look at the ball and stick model, so what the molecule actually looks like, you can see that each carbon center has two hydrogens on it, and that's actually true for all of these carbons that are in a chain. They all have two other spots, so for two hydrogens within these pictures. All right, so let's throw back to chapter 3 a little bit and think about polarity of these compounds, specifically organic compounds. So would we think alkanes are polar or nonpolar substances? So remember, alkanes, they're just carbons and hydrogens. Those are the only bonds there. So if we inspect the polarity or the difference in electronegativities of carbons and hydrogens, if we calculate that, right? So carbon, so I included the chart for you here. It doesn't matter what the number is. The electronegativity difference between atoms of the same element will always be 0. But if we calculate the electronegativity difference between carbon and hydrogen, we get that it's 0.4. And so that number is on par with what we call nonpolar covalent bonds. So if a substance only has carbons and hydrogens in it, we only see carbon and hydrogen bonds, those molecules will be nonpolar. And so that's kind of relating it to a fact of life that we run into. Typically when we think about like washing our hands in everyday life, we're using water. Water, recognized from chapter 3, is a polar substance. It's a polar solvent that we use to dissolve the grime and dirt off of our hands. But there are other solvents out there that you use for other applications. So some of my in-laws, they sometimes use gasoline to wash their hands of really grimy stuff. Like if they're working with like motor oil, Oftentimes, if you have really sticky motor oil on your hands, you can't wash it off with just soap and water. So they'll actually use gasoline to wash their hands first. And the reasoning there is because gasoline is made of mostly organic compounds, mostly alkanes, and it's nonpolar. So you're using a nonpolar solvent to wash your hands off easier than just water, which is polar. So that's just kind of an example that, composition and structure here, composition of just carbon and hydrogens gives us a different property, nonpolar properties that we can use for other applications like washing off really grimy motor oil off of your hands. Okay, so those are alkanes, the simplest kinds where it's just carbon and hydrogen. Let's start putting some other stuff on them. And so this is what we call functional groups. So we've seen some of them already, like we stuck bromine on one of our molecules, an OH group. So those are functional groups when we put things other than carbon and hydrogen on a molecule. That's where the fun comes. That's how we can functionalize, because of functional group, functionalize molecules to make them do what we want them to do. So when something other than carbon and hydrogen is on a molecule, we call that a heteroatom, so just an atom other than carbon or hydrogen. So when we have a group of atoms that look a particular way on a molecule, we call that a functional group. And so on the next slides, you'll see a bunch of different functional groups that you do need to memorize and be able to identify in a structure. So oftentimes you'll see an R on groups. So R typically means some type of CH group off of a molecule. So it really just means the rest of the molecule, where we're focusing on the functional group that we're looking at. Functional groups are really important in chemistry because that's where a lot of the reactivity comes into play. That's where we get a lot of different properties. They're the most interesting part. Just C and H's aren't very interesting. It's the functional groups that are. So here is a short list of some functional groups that you can just all see on one slide. It's missing some from in the textbook, and on the next slides I have copies of the textbook scans, but I'll put it out as a better handout. These pictures aren't very good. But what you recognize here is that there are other atoms other than carbon and hydrogen in these functional groups, and they're bonded in a very particular way. So take note of if there's double bonds or triple bonds within there and the shape that they make here. So yeah, here are those functional groups. So you see a lot of them. So if we look over here at some of these different acids that we interact with in everyday life, lactic acid, that's in milk, citric acid, that's in lemon and lime juice, the kind of, the same functional group that we see in these different substances, these acid substances, are these COOH groups. And so that is actually a carboxylic acid. So both of these substances have carboxylic acid groups on them. So you should be able to recognize that that is a carboxylic acid, or sometimes I call it a carboxy acid. It's a cuter name for it. All right. So these slides contain, very detailed pictures of what a lot of the functional groups are, and some details about, how many other carbon groups are off of the functional group. So for example, an alcohol group, this alcohol group is just connected to like the end of a carbon chain, so we call that a primary alcohol, while this alcohol, this OH group, so what we're focusing on is the OH, and there's actually two R groups, so this OH is kind of in the middle of a molecule, and then tertiary means that the carbon it's attached to has three other R groups or carbon groups attached to it. All right, so yeah, be able to recognize this. We have a couple examples coming up of identifying functional groups, and again, it's based upon both the structure and the composition within there. So we got some alcohols, ethers, so it's like an oxygen in the middle of a carbon chain. Thiols are similar to oxygen because sulfur is right below oxygen, and so sulfur will oftentimes adopt similar structures within there. So thiol is kind of analogous to what an alcohol is, but it's a sulfur atom instead. And then a sulfide or thioether. So thio just kind of means sulfur, so it's a sulfur in the middle of a carbon chain within there. So within these sulfur groups are smelly. They're smelly. We often call them mercaptan compounds because they smell bad. Okay. But I think garlic has a lot of sulfur groups on it. But we like the smell of garlic, or at least I like the smell of garlic. All right, so there are some phosphates, some amine groups with nitrogen. You see here acetyl groups or acetyl groups with oxygen and some R groups within there. And yeah, they're the rest of those. Okay, so let's keep going. So you'll just have to memorize all of those. Okay, so how else can we functionalize a carbon chain? We can functionalize a carbon and alkane chain by just removing some of the hydrogens and making either double bonds or triple bonds. So these functional groups fall under the class of unsaturated hydrocarbons. So alkanes, what we were looking at before, when everything was a single bond, those are saturated. We call those saturated hydrocarbons, meaning that every carbon has 4 bonds on it. They're saturated with hydrogens within there, that there's 4 bonds on every carbon. But within unsaturated hydrocarbons, when we form double and triple bonds, we have to remove 2 hydrogens to turn a single bond into a double bond. So you can kind of see that in this picture here. So here's ethane. There's, 4, if you look just at the black, the black bonds and the elements here, carbon has 4 bonds. So to form a alkene or a double bond between these 2 carbons instead, we remove 2 of these hydrogen atoms. When we remove those hydrogen atoms, they take 1 electron with them. And so those leftover electrons that are on carbon will form a bond instead. And that will be the second component of the double bond. So you can kind of see that here. So those 2 hydrogens go away, but these 2 electrons go between the 2 carbon atoms, and we form a double bond that has 4 electrons total between these 2 carbon atoms. And so this is why we call it unsaturated, because now we don't have the whole molecule saturated with hydrogens with all single bonds. Now we have double or triple bonds within there. So we call this a functional group because alkenes are actually more reactive than alkanes. Another atom or another group can come in and break open that double bond and form a bond with carbon and make it a single bond again. So that's why we call it reactive. Do note that the double bond has 4 electrons in it, and typically double bonds, they're always shorter and stronger than single bonds because there are 4 electrons keeping that carbon-carbon bond together. And so a typical alkene, and so then I should have prefaced this, see how the name changes. We went from alkane to alkene. All right, so the naming changes a little bit. So a common alkene that we run across is ethene. So ethane, so what I drew here, but ethane, but we remove 2 hydrogens, make a double bond. That is the chemical that fruit emits when it is ripening. And so oftentimes, like the old wives' tale, if you want to quickly ripen an avocado, you stick it in a bag with a banana because bananas release a lot of ethene gas and will ripen that avocado a lot faster. All right, so kind of on that same vein of unsaturated hydrocarbons, what if we remove 2 additional electrons from an alkene, so something with a double bond? So we can do it again to make a triple bond, essentially. Right, so alkenes were double bonds. Alkynes are triple bonds. Alkynes are more reactive than both alkenes and alkanes because we made a triple bond here. A triple bond has 6 electrons total, keeping those 2 carbon atoms together. And then on the same trend, triple bonds are shorter and stronger than both alkenes and alkanes. And so it's the same idea here. If we start with ethene, and remove 2 hydrogens and then put those electrons between the 2 carbon atoms, that's how we form the triple bond, where there are actually 6 electrons holding all of these together. So if you compare the molecular formula of ethane, ethene, and ethyne, they are all different because we have to remove electrons in order to make multiple bonds within here. Okay. And so the last type of unsaturated hydrocarbon is an aromatic compound where we have a ring of carbon atoms. So it is a 6-membered ring, and there's alternating double and single bonds. So this is benzene, the simplest kind of aromatic substance. So we have 3 total double bonds and 3 single bonds, and they're all alternating. So you see aromatic compounds really often in pharmaceuticals and molecular structures of molecules that we run across in everyday life. The reason we see it so often is because aromatic compounds are really stable. They are unusually stable. I just told you that alkenes, double bonds, are more reactive than alkanes. But benzene is very non-reactive, and there's a reason for it. Because when I said that it's alternating double bonds and single bonds, we can actually draw it two different ways. That double bond isn't locked right here. We could draw it this way where they're all alternating, or we could draw it the other way, but they're the exact same, and the molecule actually exists as in both of these states at the same time. So we oftentimes draw benzene rings or aromatic rings like this, where actually the double bonds are all smeared across the entire molecule. And that's why benzene and aromatic compounds are really non-reactive, because there's not really a double bond in the molecule itself, even though we draw it that way. It's actually just smeared across the whole molecule. And I guess I should point out here, so note that we have the skeleton structure of benzene. It looks really cute, right? But we do need to recognize that skeleton structures don't have hydrogens on them. All right, so if we inspect this, we should be able to figure out, okay, how many hydrogens are on this carbon atom in order for there to be 4 electrons or 4 bonds to a total. So there has to just be one hydrogen, because there's 1, 2, 3, 4 bonds. So just one hydrogen to make it 4 bonds. And that's what you see here in this picture in the ball and stick model, that each carbon center has 1 hydrogen on them. In order for its octet to be satisfied. All right, so on this next slide, let's test our identifying skills. So pharmaceutical compounds, they are all organic compounds. Any drug that you take from CVS, they contain organic compounds. So if you open up the packaging, that you might see the molecular structure. Typically, you'll see it as a skeletal structure like this. So we should be able to identify those functional groups. So here in these two examples, they're done for you. So ibuprofen or the EpiPen, those molecules are here. So you can see some carboxylic acids. Here is a branched carbon chain. Look, here's an aromatic ring. On our EpiPen example, we have an aromatic ring, but there's some OH groups on it that make it an alcohol. So specifically, when there's an OH group on an aromatic ring, we call that a phenyl group. And then if we look elsewhere, there's an OH group, an alcohol. Specifically, it's a secondary alcohol, because if we look at the carbon that OH is attached to, there's 2 other R groups or 2 other things other than hydrogen on it. So that's what makes it secondary. See, we don't care about hydrogen. They don't count. And then we have a nitrogen kind of in the middle of a carbon chain. So this is an amine group. And then if we look at these 4 examples, these 4 drugs are actually all painkillers of some sort. And so remember, at the beginning of the term, I said, what is the secret to chemistry? It's that composition and structure is what dictates chemical reactivity. So all 4 of these compounds are painkillers of some sort. Right? And so if we kind of inspect these and their functional groups, we see a lot of the similar functional groups. They all look kind of similar to one another, because they're all painkillers. So they're all kind of doing the same type of mechanism in our body to relieve pain. And so oftentimes if we see similar functional groups in similar drugs, it goes back to the secret of chemistry, is that composition, so functional groups, and structure is what dictates chemical behaviors. So I think right off the bat, I see these nitrogen groups on all 3. So there are all 3 of those are tertiary amines. So tertiary amines within there, all 3 of those. I see some alcohol groups on a lot of these. So there's some alcohol groups on all of them. All right, what else do I see? I see some esters on these 3, not on this middle one. All right, here's a ketone right there. Ketones on there. Oh, I missed an alcohol. I missed an alcohol right here. All right, and what else? Oh, here's another ether. I missed an ether. There's another ether right there. Oh, and there's one right there. Okay. Oh, and look, here's a little an alkene at the end. And then some aromatic rings. Also, there's some aromatic rings in all of those structures within there. So again, you kind of see the same types of functional groups in these drugs, because they have similar uses within painkillers. So being able to recognize the names of functional groups based upon molecules like this is a big learning objective in this chapter. Okay, so the very last type of molecule and functional group that we will look at is lipids, because fats, we eat fats every day, right? So fats, when we eat fats, they actually have a very specific type of structure and functional groups within the molecules themselves. So you see all these fats, all these lipids look very similar. Just some terminology here. When a fat has one double bond, we call that monounsaturated. Unsaturated meaning double bond, right? We talked about unsaturated hydrocarbons usually meant double or triple bonds. So monounsaturated means that there's one double bond somewhere in the molecule. When there's two or more double bonds, we call that polyunsaturated fats. And if you go to your doctor and talk about your cholesterol and good fats versus bad fats within your diet, these terms may sound familiar, and all has to do with the structure of the molecule, mono versus polyunsaturated. And so if we think about it, they say, like, what's the bad fat? It's saturated fats are the bad fats. So saturated fats actually have no double bonds within that. Do I have that in here somewhere? Oh yeah, I do. Yeah, so saturated fats are long and have no double bonds within them. And so we're still using that same terminology within here. So if we look at all of these structures within these fatty acids, they all have a carboxylic acid group on the very end. And there's a very unique way that we name them, and we'll talk about that in the next chapter. And so to relate the idea of fatty acids, lipids, fats within our diets, I feel like most of us have heard of the terms mono, poly, saturated fatty acids in our diets, all right? And that some different oils or fats have different ratios of saturated versus mono versus polyunsaturated fats within our diet. I did a bit of researching, and I know, so the Mediterranean diet, I wrote this down. The Mediterranean diet are diets that are high in not saturated fats, but mono and polyunsaturated fats. That's the Mediterranean diet. Because if you look at this picture, remember, saturated fats, that's the bad fats. That's what your doctor says is the bad fat. The bad fat. If we look at olive oil here, olive oil, I think, is one that has one of the least saturated fats and the most monounsaturated fats. So the Mediterranean diet, I think the whole premise here is that, monounsaturated fat is much better than the bad saturated fat. So if you eat a lot of olive oil, it's healthier. I think that's where that whole idea comes from there. And so relating this back to saturated fat and how this relates to our life, saturated fats are solids at room temperature, and you can kind of see that in these graphs here, that coconut oil, butter, lard are all very high in saturated fats, and typically if you think about those ingredients, they are solids at room temperature, and that's because they contain a lot of saturated fats. While mono and poly unsaturated fats, part of the Mediterranean diet, are fats that are typically liquids at room temperature. So there are all our different types of functional groups and structures that we'll be thinking about this term. So that kind of overviews it. And so in the next chapter video, that should say 4. I'm sorry. That should say 4. I'll fix it before I post it. We will talk about nomenclature and isomerism.